Greetings, math fans. All right, so this is day 4 notes, okay, and these are nice pre-printed notes for you. We're going to talk about a couple different things here, and then we're going to do some examples. So hopefully you have this note sheet with you. If not, write some of the stuff down and follow along as we do the several examples. All right. So basically, I'm just going to kind of read some of this, but it says in order for a function to be differentiable at x equals c at some point, it has to have a derivative at x equals c. In order for it to have a derivative, which is basically the slope of the tangent line at x equals c, there must first be a tangent at x equals c. All right, so you have to have a tangent. Furthermore, that tangent must have a slope. And just to kind of make sure you're clear as we do these problems, vertical tangents do not have a slope. Okay, just real quickly, a vertical tangent looks something like this, like that. And remember that what is the slope of a line like this? It's undefined. Okay, so it does not have a tangent at that point. All right, so let's talk about being differentiable. First of all, math fans, this is key here. This is our formal proof of differentiability. Okay, that's what we're actually going to talk about today. Tomorrow we're going to do, or the following days, we're going to talk about an informal proof. You're going to use a formal proof if you're not sure about something, or if they ask you to use calculus to show that it's differentiable or not differentiable. Okay, and that'll be like on a free response question. If it's on a multiple choice, then again, if you're not sure, you do it formally. If you know what's going on, you do it informally, and you get your answer. Okay, but just make sure you always show your work when you're taking this AP exam, because if you bypass any steps, you could lose credit for it, and it's brutal. You know exactly what you're doing, and you'll lose points for just for not doing all the steps as you should. Okay. All right, so let's look at the first guy right here. F of x is continuous. So I'm sorry, function f of x is differentiable at x equals c if, first of all, it's got to be continuous. So here it is. This is what we've talked about already. In other words, f of c has to be equal to the limit as x approaches c of f of x. So in other words, saying f has to be at that point has to be equal to the two-sided limit as you're going towards that point, and it has to equal some finite number. That's important too, math fans. It has to be some finite number. And then it says if f of x is not continuous at x equals c, then f of x is not differentiable. So it has to be continuous in order for it to be differentiable. Very, very important. All right, so that's important. And I'm highlighting a lot of stuff here. If f of x is continuous at x equals c, the one-sided slopes must be equal and finite, and you got to prove it using limits. Okay, so the one thing you're going to check if it's continuous, and you're going to check to see if the slopes on either side are the same. Those are the two things. Okay, you got that, math fans? So this guy and this guy, you got to prove two different things. All right, so that's a formal investigation. Let's talk about an informal. We're just going to make it something real quickly. First of all, you make a good sketch of something and make observations regarding continuity and one-sided limits being equal and finite or not. Again, we'll talk about that more tomorrow. But if in doubt, resort to formal. All right, so let's talk about all these graphs are going to be continuous. Okay, that's what it says. What if f of x is continuous at x equals c, but, and so here we have our different cases. One-sided slopes are not equal. And this means, and this is important here too, it's not infinity or negative infinity. Those are not, that's excluded. Okay, so if the one-sided slopes are not equal, which is right, if you look at it right there, right, when it approaches this guy, the slope is a negative slope, this slope is a positive slope. If they're not equal, it's not differentiable. Same thing. Here the slope looks like it's about right there. The slope is about right there. These are not equal. It's not differentiable. Okay, and the key to this thing here, math fans, it's called a corner. Okay. The second one is if one of the one-sided slopes is equal to infinity, and the other one is equal to negative infinity. And check this out. If I look at this, first of all, it's called a cusp. All right. So here, if I look at the slope here, if I get closer and closer and closer to this cusp, don't you guys agree that's like going to negative infinity? And then as soon as I switch over to the other one, isn't that going to positive infinity? So that's why it's called a cusp. And same thing with this one here, right? It's going to positive infinity, and this one's going to negative infinity. It's called a cusp. Okay, let's look at the next one. Again, it's continuous, but now the one-sided slopes are either both positive infinity or both negative infinity. Because here it is. Check this out. This is a positive going to positive infinity right there. And what is it from the other side? Isn't it also positive infinity? So they're both positive infinity. As opposed to this one. This one's going to negative infinity, and this one's going to negative infinity. Okay? So that is, oh, and by the way, this is called vertical tangent, which is right here. Vertical tangent, okay? So we need to check for, first we need to check for continuity, and then we can have one of three things here. I even tell you down here. For each of the following examples, decide where you think f of x may not be differentiable, and then formally investigate it. Okay, remember, you got to check if it's continuous. That's the first thing. If it's not continuous, then it's not differentiable. And then what you do is you check. We're going to check the limits. We're going to check the slopes on either side to see what's going on and to see if it is differentiable. And you're either going to tell me it's a corner, a cusp, or a vertical tangent. Okay? So let's start out with our first example. Number one, the best way to do this one is definitely with a graph. And you guys should recognize a few things. First of all, if I want to say what is the vertical asymptote, it's x equals -3. And the horizontal asymptote is y equals 0. Okay, so if I sketch these in here, that and x equals -3, the graph looks something like this. And like this. Okay, so now really what you can tell me for this one, it's discontinuous at x equals -3. So that means it's not differentiable at x equals -3. So they're going to be looking for this. Tell me where it's discontinuous. Give me the reason why, because it's not continuous, and then tell me it's not differentiable at x equals -3. Okay? Not bad. Let's look at the next one. You guys should probably recognize this one. I can factor this. So I get x plus 2, x minus 2, over x plus 2. So these guys cancel. My true equation now is x minus 2. Okay, but what did I do when I cross it off? There was a hole there. So if I actually graph this baby down 2, and then it's basically looks something like this, right? Except at -2, there's a hole. So I kind of just drew the hole in there, right? All right, so what we're doing is we're investigating. We're saying, now, what about, that's my critical point here. That's what I'm checking. And so I'm telling you guys it is discontinuous at x equals -2. Oh, by the way, I didn't really talk about what type of discontinuity. That's not a bad thought to do here. It's type of discontinuity. It's an infinite discontinuity, and it is a non-removable. Okay, and what about this one? This is a whole discontinuity, and this is removable. Okay, but since it is discontinuous there, it is not differentiable at x equals -2. Okay, those are pretty easy. Those are really drawing a good graph. That's what I'm looking for. Obviously, number 2, cancel some things out and see what's going on because you have a hole there. All right, number 3, well, this is the deal, math fans. I can't just investigate this with the graph now. I mean, it's okay to draw a graph, but what I really need to do is I really need to kind of break this up. I need to check out the slopes, and my critical value here is where that absolute value is equal to 0. So isn't it x minus 2 equals 0? So x equals 2. That's what I'm checking for. That's my critical value. Well, I can't take the limits because that's what I need to do. I need to look at the left-hand limit. I need to look at the right-hand limit. And I can't do that unless I have it turned into a piecewise function, because really it's complicated to do it with an absolute value function. So let's change it into a piecewise function. So basically what you're doing is this value here can either be a positive value or it can be a negative value. So I am going to write this as, if I write it as a positive value, it's x minus 2. So I'm going to just kind of show a little work here. Positive x minus 2 plus 2x, and that's when x is greater than or equal to 2. And it's negative x minus 2 plus 2x when x is less than 2. Now some of you are saying, wait a second, Mr. Curvis, why are you saying greater than or equal to for the one and less than the other? How do you know which one's which? Well, it doesn't really matter, does it? Okay, because you know this is a continuous function at 2. That just happens to be my vertex. All right? All right, so let's simplify this function now. So that's going to give us 3x minus 2 when x is greater than or equal to 2. And it's going to give us x plus 2 when x is less than 2. That's my nice piecewise function. All right. So now what we're going to do is I'm going to take the limit for both sides. So I can do, we can do it up here. Limit as h approaches 0 from the positive side. So I'm going to do 3x minus 2 first. So I get 3 times 2 plus h. So I'm using our slope of our tangent line, which we learned in chapter 2. Okay, I don't need to find the function. I don't need to put x plus h in there because I'm just going to have to plug a 2 in there anyway. I know that my critical value is right here, is x equals 2. So 3 times 2 plus h minus 2, right? We're just following the function 3x minus 2. And then it's minus parentheses 3 times 2 minus 2 all over h. So limit as h approaches 0 from the positive side. That gives us 6 plus 3h minus 2. Minus that 6 minus 2 is 4, so it's minus 4 all over h. So limit as h approaches 0 from the positive side is the 6 cancels with the 2 and the negative 2 and the 4. So really you have 3h over h, and then that simplifies to 3. Okay, so that's the slope of that at of 3x minus 2 at x equals 2. And let's do limit as h approaches 0 from the negative side. Okay, and then of course we're just going to plug in 2 plus h into that. So it's going to be 2 plus h. And then of course that's for x, and then it's going to be plus another 2 minus, and then it's going to be 2 plus 2 all over h. Okay, so we have limit as h approaches 0 from the negative side, and that gives you 2 plus 2 is 4, 4 minus 4 is 0, so it just gives you h over h. So that gives you 1. So because these slopes are different, you're going to say it is not, I'll write it over here, not differentiable at x equals 2 because the one-sided limits or slopes are not equal. And then you're going to tell me it is a corner. Because remember, corner is they're not the same. You can't be infinity or negative infinity, but they have to be just real numbers, and they're not the same. Okay, so that's pretty much what you do with that function, but you got to break that up into piecewise. I hope you guys understood about how to break it up into piecewise. Now I want you guys to understand, if I was actually doing this problem for multiple choice, which is not really going to happen that often, where it's this easy. If you look at the original function here, right, 3x minus 2 and x plus 2, what is the slope of that line? Isn't one slope 3 and the other one 1? Or 3 and 1? So really, obviously, you'll just look at it. If it's multiple choice, it would be really fast going, oh, geez, those slopes are different. So right away, not continuous, or it's not differentiable, because it's a corner. Okay, is it going to be that easy for a multiple choice question on the AP exam? Probably not. Are they going to have something more like a quadratic on there where you have to do a little bit more work? Probably more likely. Okay. All right, so let's keep going down here. Okay, number 4. I give you a nice friendly piecewise function, and we just have to do a little investigation of this piecewise function. So let's do that. First of all, we need to check for continuity. The other one was continuous because it was an absolute value function. This one I need to check for continuity, so I'm going to plug a 1 in there. So 2 times 1 minus 1 is 1, and 1 squared is equal to 1. So yes, it's continuous. All right, and then I need to check the limit on going from either side. So we're going to do the limit as h approaches 0, and we'll check it from the negative side first. Doesn't really matter because that one's first. It doesn't matter. We're going to have 2 times 1 plus h minus 1. And that's going to be minus, and then I'll put this in a bracket. I like brackets. Minus 2 times 1 minus 1 all over h. So we're going to limit as h approaches 0 from the negative side, and we're going to get 2 plus 2h minus 1. It's going to be 2 minus 1, so it's minus another 1 all over h. So the 2 and the negative 1s cancel, and you just have limit as h approaches 0 from the negative side of 2h over h, which is 2. So slope on the left-hand side is 2. Well, let's check the slope on the right-hand side. So limit as h approaches 0 from the positive side of x squared. So you're going to put 1 plus h squared minus, and then it's just going to be 1 squared, right? All over h. So limit as h approaches 0 from the positive side. That's going to be 1 plus 2h plus h squared minus 1 over h. Well, the 1's cancel, and I'm able to factor out an h. So I have h and then 2 plus h all over h. That cancels. I do direct substitution. 2 plus 0 is 2. All right, sweet. So this is a continuous function, and it is a differentiable function. So let's write that out here. F of x is a differentiable at x equals 1 because f prime or f of x is continuous at x equals 1, and one-sided limits or slopes are equal at x equals 1. Okay, so obviously you're not going to write anything here, are you? Okay, because everything was the same, so that works out well. Everything kind of matched up. And actually, if I would sketch this just real quickly, it actually at 1 it would join up and would meet really nicely. I believe it joins up at 1 comma 1. So when it's less than this is linear guy right here. So it's going to be something like this, linear. Okay, and then it starts to go quadratic. So it like this. And that's what it looks like. All right, that looks pretty good. Okay, let's look at number 5. F of x equals the cube root of x plus 2. Okay, well, let's take a look at what this is going to give us here. First of all, it is a continuous function. There's no reason why it would not be continuous, but our critical value is going to be x equals negative 2. Okay, you're basically setting x plus 2 equal to 0, and that's how you get x equals negative 2. All right, so let's find the derivative on each side. So we're going to do the limit as h approaches 0 from the negative side of the cube root of negative 2 plus h plus 2 minus the cube root of negative 2 plus 2 all over h. So you get limit as h approaches 0 from the negative side. Well, this cancels, right? Because the cube root is 0. And then negative 2 and the 2 cancel, so I just actually get the cube root of h over h. I need to rewrite this, math fans, and in order to really investigate this. So limit as h approaches 0 from the negative side. Do you guys agree this is h to the 1/3 power over h to the, if you want to look at 3/3 power? So I can actually write this as limit as h approaches 0 from the negative side. And can I just write this as 1 over h to the 2/3 power? Okay, now let's think about it. We have to do a little investigation here. Do you guys agree as h gets smaller and smaller and smaller, what happens to the denominator? Doesn't it, the denominator gets smaller and smaller, but 1 over some really small number is a really huge number. So truly what's going on is that number is getting bigger and bigger and bigger. But this is the key here. Okay, let me highlight this. This value right here, that 2, that is super, super significant. All right, the reason it's significant is because think about it. If I'm coming from the negative side, isn't it a negative value? But what happens when you square it? Doesn't it automatically become a positive value? So 1 over h to the 2/3 means that is actually going to positive infinity, because you're squaring a negative number and then you're taking the root of it, but it's still getting smaller and smaller and smaller. Okay. Now if you didn't square it, it would be a negative number and it would actually go to negative infinity. But this is going to positive infinity. So let's look at the next one here. Limit as h approaches 0 from the positive side. So we're going to do the exact same thing, math fans. It's exactly the same thing. So let's just rewrite it quickly here. The cube root negative 2 plus h plus 2 minus the cube root of negative 2 plus 2 all over h. Okay, that's going to be limit as h approaches 0 from the positive side. Same thing, this cancels out, and we wind up getting the cube root of h over h. So exact same thing. We're going to say limit as h approaches 0 from the positive side of, we'll just say 1 over h to the 2/3 power. So what happens now? Well, it's positive. It's easy, because isn't a positive value in the bottom still a positive value? So that's really easy. So this is also going to go to positive infinity. So the deal is positive infinity, and if you look back at your notes, if it's positive, positive, it's a vertical tangent. So you would say f of x is not differentiable at x equals negative 2, because both one-side limits or slopes equal infinity. All right, and if I would graph this function here, we can graph it up here. If I graph it, it's basically your critical point is negative 2, so it's going to look like this. So this again has no slope at that point, and that's why it is not differentiable, because you're on either side it's going to positive infinity, and there it is. It's positive infinity. This positive infinity this way, and positive infinity this way. Okay, not bad. And last problem, number 6. Okay, same thing. It's a continuous function. It's a great function, but I need to find out if it's differentiable. So we're going to say, first of all, our critical value is x equals 1, right? X minus 1 equals 0. And so let's do our limits here. Limit as h approaches 0 from the negative side of 1 plus h minus 1 to the 2/3 power minus 1 minus 1 to the 2/3 power all over h. So we're going to get limit as h, it'd be limit as h approaches 0. And that cancels out, right? And we just wanted having h to the 2/3 power. And this cancels out too. So that's equal to limit as h approaches 0 of 1 over h to the 1/3 power. Same concept as before. Now I want you to, I'm going to highlight this again, math fans. Okay, this guy right here, it's the 1/3 power. So think about it. As h goes to 0, that number gets really, really big, 1 over that number, 1 over a really small number. But now it is, oh, and I didn't keep this negative here, but now it's not, it's staying negative. So you guys agree it's 1 over some really, really small negative number. It's like saying 1 over negative 0.00000001, which is some huge negative number. So that's why this is approaching negative infinity. Okay? And if I do the same thing, limit as h approaches 0 from the positive side, I'm going to do 1 plus h minus 1 to the 2/3 power. And then it's minus 1 minus 1 to the 2/3 power all over h. So again, all this stuff cancels out, and I wind up with limit as h approaches 0 from the positive side of h to the 2/3 over h. And I can rewrite that as limit as h approaches 0 of 1 over h to the 1/3 power. And of course, this going to the positive side. Positive is easy. It's always positive. So that's equal to positive infinity. So here we go. We have negative infinity. We have positive infinity. So what is this? Okay, we're going to say this is a cusp. And so f of x is not differentiable at x equals 1 because basically the one-sided limits are not equal. Or I really better say one-sided, because one-sided limits are negative infinity and positive infinity. So you're going to say this is a cusp, which I already did down there. Okay? So all these things I just did here, math fans, these are all formally proved that it's not differentiable or that it is differentiable. Okay, it's all with limits, except obviously if I did those first that first problem, right? That wasn't even with our first two problems wasn't with a limit, right? It was just graphically, and that's fine as long as you show me a good graph. And then when we went on, like for number 3 all the way through 6, that was all formally where you're actually you're showing me the limits, what's happening to the left and the right of it. Okay, if it's a piecewise function, got to check for continuity first. If it's a continuous function like one of these last several functions, or an absolute value function, continuity is not important because you know it's a continuous function. You really need to check the limits on either side to see if the slope is the slopes are equal. Then it's going to be differentiable. All right. All the homework tonight should be done by basically the long way by showing me formally that it is differentiable by showing me with limits and whatnot. All right. That's it, math fans. Have an outstanding day. Adios. Goodbye.